All right, we're back. Cool. Inertia, yeah, okay. Yeah, Particles want to continue moving the way they were moving, and so like they resist change, just like we all do when moving around, right? Thus, the first part of the velocity update takes into consideration its current velocity. All right? So velocity, so the first part is this, where I is some particle. There's a swarm of particles, right? So I is just one arbitrary particle. Velocity of time t is like, well, the velocity at that instant, okay? And w is some coefficient used to control, it's one of those tunable parameters. It's used to control how much the particle wants to resist change. Typically, you're going to see it between 0 and 1. Okay? You could make it whatever you want, but you're really going to want to make it between 0 and 1. Okay? If you crank it to 1, it's really going to want to keep going the way it's going to go. Right? If you crank it down to 0, you can spin on a dime. All right? Then we have the cognitive term. This, I don't know why they named it this, but it's the cognitive term. This is the fact that each particle wants to move towards the area of the search space it prefers the most, based on its like best that it remembers, right? Its best known location. So what is this calculation? Well, it's this. So, but what are these things? Simple. All right. So I is that particle. This is what I remember the best was, and this is where I am. Okay? So the further away I am, the bigger this becomes, right? The bigger the the further away I am, the bigger the difference, right? And then we've got some coefficients, C1 and R1, okay? C1 is some coefficient to control how much we want to be influenced by what I like the best, okay? You crank that up, I'm going to be more likely to move towards what I like and not worry so much about what the other particles are doing, right? That's the idea. And that means assuming that the other one stays the same and we crank up C1. And then R is some randomness that we're going to add to it, okay? There's still some stochastic nature, and we're going to add just a little bit of randomness. Now, in terms of C1, usually we're going to have values of between 0 and 2. You can do whatever you want, but that's usually what you're going to want. And yeah, so the higher the C1, the more we're going to be influenced by what I want to do and not what everyone else is doing. Okay? Yeah, this is some random vector, so we just call like Python, like math.random, right? To get some random values to just sprinkle into there, right? To scale it a little bit. R1's the stochastic, that's the best one I know, and this is the current position at time t. The difference between the particle's best known position and the current position dictates where the particle needs to go, right? So, like for example, and these ones just scale the vector. They're scales. Okay, they scale it. Cool. So, if I am here, and that's the best I found, that's the vector, right? And then I can scale that vector up and down based on the randomness and C1. Right? Nothing crazy. Do you see? Yeah, cool. And then the social term, it's the same thing. Just instead of my best, it's the global best. And what I'm going to do, well, C2 and R2. C2 is R really a vector? Or is it just, yeah, sure, why not? C2 is that cognitive term. Dial it up or down. Assuming C1 is left unchanged, but we crank C2 up, we're going to be more influenced by what everyone else is doing. If you dial it down, we care less about what everyone else is doing. Okay? G is the global best, and X at point T is the current position, right? And then, okay, R1 and R2. The cognitive and social portions of velocity update includes the R1 and R2 vectors. These vectors have values between 0 and 1 that are stochastically determined. Remember, stochastic is just a fancy way of saying random because we don't like the word random. Randomly determined for each velocity update calculation for each particle. So this is always, there's always going to be randomness involved. All right? These random stochastic vectors are important as they add like that chance of like novelty and like a little bit of like explorationness to the search space. And if you don't have, like at the end of the day, if you don't have them, like we can demonstrate pretty easily that this isn't going to work very well. We need a little bit of that randomness, all right? So that's what I mean there. Like empirically, if you don't have them, it's going to converge too early. We like it to just have a chance to kind of like go elsewhere, all right? Yeah. And then putting it all together, well, you get this. Now, if this looks intimidating, it's just the sum of its parts, okay? And this is how like vector arithmetic works, right? So the velocity of a particle, and right now we're only talking about the velocity here. We're not updating the particle's position yet. That's the next step, which is hilariously simple, but we'll get there. The velocity at the next iteration is going to be based on how fast I'm going, scaled by my like inertia, plus how much I want to go towards what I saw, plus how much I want to go towards what everyone else saw as the best. Okay? And then all of the nuance that we talked about each of the parts still applies. For example, like the C1, the C2, the randomness, and like, well, the further away I go, the more I want to go toward, right? Like, I really want to go back there, oh man, right? Like that idea still stands. So that's how we update the velocity. If this looks crazy, once you see the code, you'll be like, that's it? Yeah, okay? Now, for a moment ago, we like all these vectors. Well, how do you set what they are? Well, it turns out that some guy named Vandenberg, in their thesis a long time ago, I don't think it was that long ago, found that these numbers just work really friggin' well, and it seems like this is like the standard. You just use these values. How did they find them? I'm not even 100% sure. I didn't read the thesis. All I know is that everyone's like, yeah, use these ones. Okay? So on the plus side, yes, they're tunable. You can change these values to whatever you want. Someone's kind of done a lot of heavy lifting for you where it's like these are general purpose good values, okay? What should the inertia be? That. What I find hilarious about this is that's oddly specific, right? Like, nope, not 729843. No. Right? Like that I find amusing. I'm sure there's some amount of method to the madness. I'm just trusting it because everyone's referencing it. Hopefully I'm not a fool. And then C1, C2, 1.496180. I find it amusing that the zero's there to let you know, like, no, this is precise, right? Like, whatever, fine. There we go. You use that value. Awesome. And it's shared among C1, C2, meaning you're like equally influenced by both. All right? But again, you really should aim to do some amount of tuning on your own, but this is a great place to start. Any questions up until now? I realize this might be hard to kind of like tie to anything concrete until we see a concrete example with code, but hopefully it's not too crazy, the abstractness here. We'll tie it all together in a moment. But any questions? All right. Position update, easy. Add two vectors together. Add the position plus its velocity, done. All right? So you take its current position, what its velocity is for the next step, boom, that's its next step's position. Easy peasy. So consider the below figure. Cover the new position can be determined. The new position is the sum of the current positions, current velocity. Cool. Yeah. Although I suppose I say current velocity, it's like the updated velocity, right? You update its velocity, then you update its position, right? They kind of go hand in hand. And if you wanted, you could kind of like substitute all of this, like with this part, right? So really, it's its position plus all of this at time t, if that makes you happy. All right, so here is an example. The particle's current position, xi, is represented as a green vector. Well, not really the green, well, I guess the green vector, yeah. There's its position, okay? The particle's velocity is represented in the blue vector. This is its velocity, okay? Okay? So where's its position going to be? You add the vectors together. And if you've passed grade 11 math, you've done this? It's like grade 11, right? Yeah? Maybe grade 12? Come on, you remember learning this though, right? Adding vectors? No? Oh my goodness. Here's what you do to add, okay. this is important, and please don't assume I'm just going to ask. Raise your hand if you don't know how to add vectors. It depends. Okay, you know what? Then maybe I'm being ambiguous. What do? You literally just add the parts together. Okay, if you have vector like A, B, and then like X, Y, right? You want to add them? Well, the result is A plus X, B plus Y, right? And then what does that mean in terms of like visually? This marker's not the best. I'm running low on markers. I think I leave them in here and then people walk away with them. If you've got some vector like this and another vector that's like this, for example, okay, two vectors, because vectors always originate from like the origin, right? If you want to add them together, you do like, actually no, to like, assume this is the same size, right? And then the new vector will be, right? That's how it works, right? I feel like you learned this in like grade. You remember learning this in like math class in high school? Yeah? Okay, anyway, whatever. Doesn't matter. Anyways, if you take this green vector and you add the blue vector, you get the red vector. Boom. That's where it is. So, and by the way, too, don't get too thrown off here, right? You might be like, vector? What's with the vectors? These are points in space. Yes, but if we treat the points as vectors, then it's just like, okay, whatever, right? But really, at the end of the day, yeah, you're adding points, right? But, you know, okay? Yeah, yeah, yeah. Yeah, anything else here? Okay, yeah, so, yeah, the sum of the particles' current positions and velocity, 3, 2, 3, 2, plus negative 1 and 1 is, ooh, oh man. Is 2, 3. Why? Well, 3 plus negative 1 is 2, and 2 plus 1 is 3. Right? Cool. All right, the algorithm. This is it. I know it's pseudocode, but this is it. Initialize the particles' positions randomly. That would be like the full swarm, right? Initialize the velocities randomly within like the bounds that you want. Then, while stopping criteria is not met, for all particles, evaluate the fitness. Just pump it into that function that I just deleted. Okay? Update the particles and global best if necessary. Okay? This is where you do like each particle's best known and each particle's like, or the swarm's best known. And then, again, so you do that for everyone before you update anyone's velocity or anything. Then, for all particles, calculate the particle's new velocity, update the particle's position. That's it. And really, like I showed you could do this on one line, whatever. That's it. I know like GAs are really simple too, but like it really is pretty friggin' simple. But like I was saying, like look, and by the way, and I know I'm recording myself saying this, so this is like I'm opening myself up for making people very angry, because PSO people will be mad at me when I say this. It's just a GA though, okay? And that's not a bad thing, but because like remember, evolutionary computation is a loose framework, right? So like everything's the same, okay? But why? Well, look, there's initialization, there's that like generational loop, fitness evaluation, and then the variation operators. But the variation operators are kind of like what's special here, right? It's like, well, how we update the positions effectively, ultimately, that's like the variation operators. They're still variation operators. If you were to say like, oh, it's crossover, well, yeah, and no, right? Like it's not like a clear crossover, but also remember how like we talked about some of those like floating point crossovers when talking about real number things and like GAs, how some of them were like take two chromosomes and like find the average between the two. There was no like explicit like splicing and copying and pasting. Like you couldn't, like the crossovers are just being influenced by other things, okay? A mutation is like being influenced, like something internal, right? So like, it's still variation operators by definition, okay? If you're looking for like where, well, I don't see like 1-point crossover here. Well, yeah, it's not, but it's still the same idea with the variation operators, okay? The major difference is, yeah, there's no real selection, fair enough. There's no selection, but that's just because like the selection strategy is, well, everyone survives, okay? In the same way that the like replacement selection strategy in a generational generational GA is everyone's replaced, right? It's all just framing. Although, yeah, there's no real selection as all particles survive, but this is a selection strategy. And the velocity and position updates are not mutation and crossover. However, consider the cognitive and social aspects of the variation operators. This is a mechanic for exploration and exploitation. In other words, they are, in fact, variation operators. Enhancements, like all forms of evolutionary computation, like I said already a billion times in this lecture and in previous lectures, it's whatever the hell you want to do. And you just try things, and if it works, it works. Chances are, too, like you try something, they work, right? As long as there's like good intuition to it, and you can find out easily by testing your ideas. Because look how simple this is. Easy to add things into. And that's a good thing. Simple doesn't mean trivial or not effective, okay? We like simple. We really want simple. All right, so PSO, this ability to be modified is part of the reason why it's so popular, like most other forms of evolutionary computation. Here's some quick ones. Neighborhood, okay? Well, okay, so we've got, everyone's influenced by themselves and the whole swarm, but like what if we had like subswarms, right? I'm a bunch of birds, right? Like there's a bunch of birds, right? And I'm a bird, and I want to go where I like, and I want to go where the swarm goes, but I also want to be influenced by like where my best friends are going or something, right? So like you could have like sub-swarms. So perfect, great. Add another one, right? C3 and R3, right? So there you go. We've got, here it's called like a neighborhood. So it's not the whole swarm, it's some subset. And you might have multiple neighborhoods, right? Maybe it's not even like mutually exclusive. Some things could be in different, whatever. The point is, you could do this. And you could do this forever. You could have like scales. Depending on how big you're going, maybe you have like nested neighborhoods or something. And if it works for you, great. Awesome. That's the beauty of this, okay? Yeah, and there. That's the neighborhood's best. Cool. All this requires is one more part of this weighted sum. And we need to also keep track of then, like here, like update the particles and globals best. Fine, update the particles, neighborhoods, and global bests. Cool. Cool. Velocity clamping. This one is basically like your standard enhancement. If you don't have this, you're probably not going to have a good time. So maybe even calling this an enhancement isn't quite right. Velocity clamping. Just set like a speed limit, right? When you're doing these calculations, it could, like things can go weird, and suddenly like your particles end up getting velocities of like a bajillion. And then they're like all over, and you're like, okay, no, let's just, okay, you can cap out at like whatever number of units, okay? So it disallows it from things going like way too high and then going to areas of the search space where like they really don't belong, okay? This could be done by setting ceilings or some like exponential decay, which is nice. There's a lot of ways too, like you can have it so like, well, maybe you don't just like clamp it, but maybe you say like, okay, at each step, the velocity also has another term, which is some like exponential decay or something, where like it just keeps like, it keeps being like a friction parameter, let's say, okay? Where yes, it's got inertia, but it also has like a friction or something, right? So you could add that in. And then boundary position clamping maybe like you don't want your particles to go outside of some area of the search space, right? Like if you know your search space, like imagine, and this is not likely the case, but imagine like, okay, here, we're showing what this function, some magic function, looks like between -3 and +3 in both dimensions. For all we know, like, and I want to find the minimum value, right? For all we know, maybe once you just get past here, it's like concave or something, where like, okay, it just goes like this. Okay, like as soon as you go out here to points past like 3, it just starts to come out really bad or something, right? So if you know something about the search space, we're like, look, those areas, like you do not belong anywhere else other than in this area. I know the best is somewhere in here. So you clamp it. You set boundaries where you say, just don't let them go beyond the boundaries. How? Well, you can set limits. Maybe you have it such that, like, okay, if you go past the boundary, your velocity gets updated. So, like, your inertia can make you go past the boundary a bit, but you'll get sucked back to where you belong. Maybe you just do, like, hard limits where you go, like, no, boom, you can't go past here, right? Your velocity gets destroyed, but then, okay, you can start again by being influenced by the social and cognitive aspects, right? And you can have like more creative strategies. Like I've seen people do like bouncing where it like bounces off. Okay, cool, why not? Or like have it like just like wormhole to the other side, which is kind of fun, you know, like pretend it's on like a sphere, so you just kind of go around and like boop, you show up on the other side. Cool, why not? Do whatever you want. If it works, good. If it didn't, whatever. It's trivial to do. And then like a really cool one too is a buddy of mine, I can't remember if they like invented this. I feel like they did. I could be misremembering. So back where I did my undergrad, there was like a big group of people that did PSO stuff, right? Anyways, I think a buddy of mine invented this. Maybe they didn't invent it, but either way, it's the idea that like, well, the particles actually want to repel each other a little bit. Okay, so you actually don't want to allow them to get too close to one another. Right? Cool. And what's the value of that? Well, if all the particles are going to the same point, you're actually kind of like losing like diversity effectively. Like look, right? Yeah, sure, they're all like near the optimal, great. But like see how they gather right to there. They're like on top of each other, right? But if they all kind of like repel each other a little bit, to some degree, I mean, this is real numbers. If I zoom in, they're not all exactly on top of each other. But if you wanted them to repel each other just a little bit, you might get a better view of the search space, which then gives you better local and swarm bests, which then makes better and so on and so on and so on, right? And if I remember this story correctly, I think I remember, and this would have been like 2012 maybe, I want to say. I'm pretty sure the story goes that there were two people in the same research group, the same lab. One person was working on a PSO, and the other person, they do PSO stuff too, but they were implementing a simulation of evacuations of like a building. And the people in the simulation, people don't want to bump into each other. So they built in some mechanic where they don't bump into each other. And then they were like, well, actually, no, you should actually maybe throw this into PSO. And then they did that, and suddenly it was like, whoa, right? Or maybe I'm getting it backwards. Maybe they took the charged PSO and then put it in their simulation. Either way, whatever. It doesn't matter. Charged PSO, it's cool, right? Great, awesome, awesome. And then, yeah, there you go. What is this? Check out the following script, selection script. Is that right? It doesn't seem right. PSO, yeah, that's a typo. That should be the PSO script. Keep. Open. Actually, let's do this real quick. Perfect. Delete, 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 connect. Could probably do this in here pretty easily. Can you see that okay? I know it's not the best, but you might look at this and be like, whoa, what's going on? Okay, the next class is going to go into this, right? I know we're going to be out of time. We're not going to start the next one. But here's PSO, okay? It uses NumPy. I'm pretty sure Colab has NumPy. Awesome. And I'm doing it on Colab because, again, I don't know, my computer hates Python now, apparently. Here's all the values I have. Function dimension 2, starting bound positions and velocities, number of particles, iterations, inertia. I just took it from that thing. Cognitive and social, I made sure to include the 0, I guess, which I find amusing. These are just hyperparameters. And I know you're like, wow, that's a lot. Not really, right? Like, what do you have? Like, okay, well, the number, that's the function that you want to optimize. Yeah, these are just starting things. Great. These were kind of set. I mean, really, like there's really actually not a lot to tune there. It might look like it's not a lot. It's definitely not like a GA where you're like, well, what do I want this K to be for my selection? But then what about how much should my crossover rate be? Because my mutation rate, right? Like you don't have as much. So there, nice and simple. Here is the function I want to minimize. Here is some function, okay? Why do I want to minimize this? That's not the point. I just want to. This could be anything. It could be a black box. I don't care. But here is a function. It takes 2 inputs, all right? And I want to know, given which 2 inputs gives me, here I think I'm minimizing, which 2 inputs gives me the smallest number. Or maybe I'm maximizing the biggest number, right? So I put in an x and a y, this function gives me back a number. What is it? If I give it a different x and y and it gives me back a different number that's smaller, I like it, okay? Or bigger, I like it, depending on if I'm minimizing or maximizing, I can't remember. But do you see, that's just a function, right? If you're like, well, what's the connection here to a GA? Well, there's no like direct one because with the GA, like this would be like the fitness function, okay? Where you go through, calculate the Hamiltonian cycle, right? You could do, if like I'm thinking, like what is a basic, like, whatever, I don't want to worry too much about it, but anyways, cool. There's the function, you see? And then here we've got this. Again, if you're not a huge Python whiz and you're like, what is this? All this means is, a lot of people are like, oh, that means it's the main function. Well, actually, not really. What that means is if you run this code, and it's not like what I'm explicitly running, what I'm saying run, don't run this. And you're like, well, why? Well, because if I like imported this code somewhere, whenever you import code, it runs the script. And I don't want this to run if it's been imported, even though I'm pretty sure there's no reason to import this code, except for maybe this, but nevertheless, there you go. All right, initialization. Particles for whatever in range of the number of particles, create the particles. I'm doing it, you might think like, oh, make an object. Look, here's another software engineering hack, okay? If you've got an object that just needs to be data, use a dictionary, okay? These are your fields. These are the values. I don't need any functions on these. I don't need any methods, right? So don't go to your way to make a new object, just use like a dictionary. This is a common thing, okay? So there you go, position and velocity. How are those found? NumPy random uniform based on what I set, those hyperparameters, okay? NumPy random uniform, whatever, okay? And like, why do I have to do, well, okay, look, function dimension. This will give me back a vector, I'm guessing a NumPy array, of like a 2-dimensional here because function dimensionality was 2, right? So I want, right? It needs a random x and y and a random x velocity and y velocity. And then particles' best known position. Each particle also has a best known position, which is its current position. And then particles append to particles, cool. And then the global best is just take whatever the first, it doesn't matter, right? The global best, whatever. I guess I could say go through and evaluate each ones and update it, but who cares? It's the first one. It's all going to get obliterated instantly anyways. So for each iteration, for each particle, run it through the function, Did we talk about this before? When you put a star here? No? This means like particle at position, okay? If you go up here, the particle's position is a two-dimensional iterable, okay? This function requires two values. But particle at position is like an array of two values. So if I give it to that function, it's going to be like, I needed 2, you gave me 1. You put the star there, it means like unpack. Like, okay, don't give it the one thing, give it the things inside. That's what that means, okay? So call the function. If the new value is better than the best, update it. If it's better than the global best, update it. That's it. Then go through, get your randoms. For the velocity, that's the calculation, okay? Inertia times particle velocity plus cognitive R1 times the best known minus that, plus the social R2, the global best, that. Now, why is global best not in the dictionary? Because there's only one global best, but each particle has its own best known position, right? That's it. And then how do you update the position? Add those two things together. That's it. That's literally it. Now, at the end, right, all this does is give you like an XY of the best one you found. And if you want to know, like, well, what was its value? Like, here's the global best, and we'll like, okay, what is the function at that global best? Fine. But if I hit run, boom, there we go. Right? There, I got a really small number. I'm pretty sure the best value, so by the way, I realize we're out of time, but I'll take 2 more seconds to say, I'm pretty sure the best value is 0, 0, right? Now, times 10 to the negative 6 times 10 to the negative 5, very friggin' close to 0, right? But why is it not 0, 0? We're dealing with real numbers, right? It is what it is. You ain't gonna land on 0, 0. It's not gonna happen, right? You're gonna land on things really friggin' close to 0, okay? Times 10 to the negative 6, that's small. Any questions? Awesome. Have a wonderful weekend.